The midpoint rule is similar to something that was discussed in the last section regarding using midpoint rectangles in order to approximate the area under the curve. And so here is an approximation for the integral, since again that relates to the area under the curve. So we can approximate the integral from a to b of f of x dx by taking the summation here of f of xi bar times delta x. And then it also shows the expansion of the summation where delta x equals b minus a over n and x bar sub I equals 1/2 x I minus 1 plus xi, and that's equal to the midpoint of the interval from xi minus 1 to xi. We're going to use this idea to approximate the integral from 0 to 1 of the square root of x cubed plus 1 dx. So according to this, the integral from 0 to 1 of the square root of x cubed plus 1 dx is approximately the summation I equals 1 to n of f x bar I dx. And that's equal to delta x times f x bar 1 plus f x bar 2 plus ... all the way up to f x bar n. So let's use the formulas that they have laid out up above there, where delta x is equal to b minus a over n. Here again, b is the upper bound of integration, and a is the lower bound of integration. So this would look like 1 minus 0, and we're going to be using n is equal to 5, so over 5. So that'd be equal to 1/5, and that corresponds to basically the width of the rectangle. So it might be helpful to kind of get an idea of what's going on with the function using these 5 rectangles. So let's go ahead and lay out a picture. It may not be exactly the function, but I'm going to think about what the rectangles would look like with the 5 rectangles we're talking about here. And that'll help me lay out the different values that I need to use. So we're using the midpoint rectangles here from 0 to 1. So it's going to look something like this, depending on what the graph looks like. But what this is good to know is how the numbers along the x-axis are constructed. Since we know delta x is equal to 1/5, we have here 1/5, and then we're going to go to 2/5, 3/5, and 4/5, all the way up to basically 5/5, which is equal to 1 at the very end. And this is basically corresponding to x1, x2, x3, x4, and x5. And I guess we'll consider also the first one as x0, which is also a. Now in the middle is where our x bar is going to be located. That's corresponding to the midpoint location. So x bar 1, x bar 2, x bar 3, x bar 4, and x bar 5. So what I'd like to know is what are the numbers for each of those locations all along in the middle. So it gives us basically a formula for doing that. X bar 1 is going to be equal to 1/2 of x0 plus x1, and that's going to be equal to 1/2 times 0 plus 1/5, or 1/10. So that x bar 1 in the middle is 1/10 basically. And we'll do that for the rest of them here. X bar 2 would be equal to 1/2 of 1/5 plus 2/5. That's going to be equal to 3/10. X bar 3 would be equal to 1/2 times 2/5 plus 3/5, which is going to be equal to 5/10, or I guess just 1/2. And x bar 4 would be equal to 1/2 times 3/5 plus 4/5, equal to, and that's going to be 7/10. And then finally x bar 5 is going to be equal to 1/2 of 4/5 plus 5/5, which is going to equal to 9/10. So what the midpoint rule is going to tell us we can do with these numbers is integral from 0 to 1 of the cube root, or I should say, sorry, the square root of x cubed plus 1 dx is approximately equal to 1/5 delta x times f of 1/10 plus f of 3/10 plus f of 1/2 plus f of 7/10 plus f of 9/10. So if we plug in, again, our function, something like f of 1/10 would be equal to the cube root of 1/10 cubed plus 1. We can do that for all of them down through here. And I just went ahead and plugged that all in the calculator and approximated it to a function value and an integral approximately of 1.109673.